Qubits and chill, relax. It's just linear algebra with drama.
Welcome to Season 0, Episode 2. Today, we'll set up our quantum lab on Windows, Python, Qiskit, and Jupyter Notebook. I'll also explain what each tool does so you actually know what you're installing. Firstly, we need to install Python. Python is the programming language we'll use to write and run quantum circuits. Let's download Python from the official website. Download the latest version for Windows or Macintosh or Linux. You can find in YouTube how to install Python and other operating system. When download is complete, you open it and install Python. I installed Python before, so I don't reinstall it. I just remind that checkbox is important. It lets Windows find Python from the command line. You need to select add Python to path. It's important. Okay. Now we need to control the Python is installed. The terminal lets us run commands to install libraries and test our stuff. Let's test the Python. As you can see, we have the Python. Okay, I have Python and pip. On some Windows systems, Py is the default Python launcher. Sometimes you need to use this. Then we need to create a project folder to keep everything clean and organized. Then we need to create a virtual environment. A virtual environment is an isolated Python workspace. It prevents package conflicts and keeps this project separate from everything else. To create a virtual environment, you use this command. Just a minute. Python mvenv dot venv. Then you need to activate the virtual environment, and you can activate like this. Okay, I forgot the dots here. As you can see, there's a dot venv. If you see dot venv here, the environment is active. Then we need to install Qiskit. Qiskit is the quantum computing library we'll use to build circuits, simulate them, and later run them on real quantum hardware. For install the Qiskit, pip install Qiskit. Let's test the Qiskit is installed or not. As you can see, this confirms Qiskit is installed and working. Then we need to install Jupyter Notebook. Jupyter Notebook is an interactive environment where we can write code in small blocks, run it, and instantly see results like circuit diagrams and histograms. For installing the Jupyter, we write pip install notebook. After that, let's run the Jupyter Notebook. Jupyter Notebook. This will open a browser tab where we can create our first notebook. Let's create the first quantum circuit test. Just it's just a demo. This is our first sanity check. We'll create one qubit, apply a Hadamard gate, measure it, and see a roughly 50-50 result. Let's create our first test code. You see, no model name Qiskit AER. You you need to install pip install Qiskit AER. To install the Qiskit AER, let's go back to Jupyter Notebooks. So let's run the Jupyter Notebook here again. First, I will explain this code. This code is a basic Hello World quantum circuit in Qiskit. It creates one qubit and one classical bit. applies to Hadamard gate to put the qubit into superposition, then measures the qubit, runs the experiment 1000 times, collects the result, and plots a histogram of outcome. Let's look at the code step by step. From Qiskit import quantum circuit. Quantum circuit is the object we use to build quantum circuits, qubits, gates, and measurements. From Qiskit AER, import AER. AER provides simulators so we can run quantum circuits on a classical computer without real quantum hardware. From Qiskit visualization, import plot histogram. This function helps us visualize measurement results as a histogram. Then we have creating a quantum circuit code. This creates a circuit with one qubit quantum register and one classical bit classical register. The classical bit is used to store measurement results, 0 or 1. Then we apply the Hadamard gate. This applies an hash gate to qubit 0. We'll see the Lex lectures, I guess, the Hadamard gate, so I don't go into details. That means when we measure it, we get 0 with 50% probability and 1 with 50% probability. This is like superposition. Then we measure the qubit. This measures qubit 0 and stores the result into classical bit 0. Measurement converts a quantum state into classical outcome, like 0 or 1. Here we choose the backend simulator. A backend is where the circuit runs. The Chasm simulator is designed for circuits with measurement and return classical results like 0 or 1 counts. In here, we runs the circuit 1000 times. In quantum computing, outcomes are probabilistic, so we repeat the experiment many times to see the distribution. And here, we get the measurements result. This returns a dictionary like outcome 0 happened 500 times, outcome 1 happened 500 times, so the result is roughly 50%, 50-50 as expected. Then we draw the circuit. This displays the circuit diagram using matplotlib. You will see one qubit line and hash gate, a measurement operation. Then we plot the histogram. This plots a histogram showing how often 0 and 1 appear. You should see two bars close to same height. Let's run this code and see the outcome. Remind that sometimes some models cannot be installed, so if you see an error, just install its model, then problem is solved. Now, look at the histogram. The histogram visualizes the same data. Each bar shows the frequency of measuring 0 or 1. Since the bars are almost equal, it confirms that the qubit was in a superposition before measurement. The circuit applies a Hadamard gate and then measures the qubit. The counts show how many zeros and ones we got after 1000 shots, and the histogram confirms the distribution is roughly 50-50. It won't be exactly 50-50 every time because measurement is random. But as we increase the number of shots, the result gets closer to 50-50.